Okay, actually, now that this thing has started, I'm going to begin this with. Perfect. That should pick up pretty good. So, physical science time. Today we're talking about electricity. If you write that in cursive, you have to really think pretty hard about where the T's and the I's are. Electricity. I think I got it right. Excuse me. What up with electricity?
It can shock you.
Okay, it can shock you. What else?
Just got shocked the other day.
Josie got shocked the other day. What else?
She wasn't wearing shoes.
Okay. What else is true of electricity?
It can power something.
What force is behind electricity? Well, we talked about the four fundamental forces of the universe. There are only four forces in the universe. What are they?
Gravity.
Okay, gravity is one of them. Yeah. Is gravity what's behind electricity?
No.
No. Okay. So let's list our four fundamental forces. What's the strongest of the four fundamental forces? Do you remember?
Gravity. Electromagnetic.
It's neither of those.
The force.
Good thing we're all paying really good attention because this is kind of important. There are four fundamental forces in the universe. What are they, from strongest to weakest? What was the first
Gravity?
one? No, that's the
Okay.
weakest.
Okay.
So let's start from the other direction. Let's start from the strongest.
Magnet. Magnet.
I think you have this in your notes if you go back and look a little ways.
How far?
I just couldn't say. Friction isn't one of them. The first one starts with the word strong.
Strongism. Strong water.
I know I've told you this before. I have video evidence that I've told you this before and you have forgotten it. And that's okay. It's okay to forget things. So far, to recap in this video, we have drugged the stool across the room for a little while and then asked a question that seems to be unanswerable. And talked about how hard it is to write electricity in cursive. We're really on a roll. The answer that I'm looking for, and you should write this down because it's apparent to me that not very many of you have this in your brains, if any. The strong nuclear force is the strongest of the forces. The next one in order is electromagnetism. The next one
I said electron.
is the weak nuclear
The
force.
first one was.
Whatever.
And the weakest of the four fundamental forces is gravity. Each of these has its own force constant that goes with it. In electromagnetism, we call that constant K. And in gravity, we call it capital G. You remember, I hope, that capital G is the quantity that relates the distance between objects and their masses to the force of gravity between them. We did math with this one earlier in the year, and now we'll do math with this one. So electricity is one aspect of electromagnetism. Can you guess what the other aspect of electromagnetism is? Magnetism. Those two areas of scientific thought are really one force, electromagnetism. Furthermore, the idea of light is also electromagnetism. In so much as that's a force of the universe, it is also how we perceive with our eyes the world around us. But we'll talk about light and magnetism later on. For now, we're talking about electricity. And as Lucas correctly pointed out from Google, there are two broad categories of electricity that we talk about. They are static and current electricity. Static and current electricity. And the objective is to relate those together and to tell the effects of them. Compare and contrast the types and effects of electromagnetism. Compare and contrast the types and effects of electromagnetism. So the part of the objective is the types of electromagnetism. Does it say electromagnetism? Yeah. the types of electromagnetism, and that's these two. So can we compare and contrast those? Well, not without a little bit more information. You've heard of static electricity.
Yes.
That was not even a question. That is a statement. You have heard of static electricity. And in what context have you heard of static electricity? Give me an example.
Balloon and hair.
Balloon and hair. Guess what, Lucas? I have that example right here. I have balloon, and I still, to this day, have hair. Have you ever seen this one before?
Yeah, we did it on Josie.
No, I have. I forgot to do picture-in-picture there. You should be able to see. My hair isn't very
Hair.
little. I don't know what you call it. What is it doesn't? Do you see it?
Thin.
Do you see it? Is it moving?
No.
No, I just think I got a mohawk.
Well, that's probably because of the rubbing. That's probably less because of the. Is it pulling my hair up when I do that?
No.
Make a girl go.
Why don't you go, Safer, you go get another balloon so we can have someone with thinner, longer hair. Usually you can see it pretty well, but maybe I need to rub harder.
He's not doing that.
There, you kind of can. You can tell a little bit.
Do it on Josie again, that'll work.
You guys not remember?
I do, but no.
Why? Just
Sometimes.
We have to do it.
So I have a pretty good, or I think pretty good video when I showed this stuff to the 8th graders that you can really tell it now. I can feel it. Where it sticks to the, whoa, that's the opposite of sticked. That just slid right off. I hope we can get another balloon. That place is like a black hole for students. They cannot, once they go in there, they cannot find anything. It's like people lose all
Let's
their
just
money.
like paint to save them. Yeah. They gotta go save her.
Did you find a balloon? Very good. Who would like to be on the public YouTube video? You have signed a waiver, but I'd like to ask you
It has to
anyway.
be a woman.
I think
But we
maybe
need a
Cody
girl.
will work.
No.
Women's hair.
Josie.
No.
Yeah, use Josie again.
Cody.
Sure.
Cody and hair will work.
Cody will do it.
Cody got woman hair.
Remember that the new microphone, or the microphone we're currently using here every single time you say it. Here, now,
Use Pam. She has long.
let's think about that for a second. First, let's diagram it. And I'm going to leave that balloon there for use in a second. But static electricity, what's happening when I hopefully get someone to? There's a balloon. Both the balloon and the hair. This is my hair, by the way. That's me. But angry. Both the balloon and the hair are made of what?
Adams.
I'm about done asking you guys questions. Yes,
Electrons.
atoms. And the atoms are made of
Electrons and protons.
electrons and protons and neutrons, right? And of those, the portable one of those, I mean, all those things are movable and they're very, very small, but the one that can most easily move from one object to another is the electron. So when I rub the balloon on my hair, either the balloon is transferring some of its electrons to my hair or the other way around. It doesn't really matter because, or it doesn't matter which one of those happens, but let's say the balloon is transferring electrons from my hair to the balloon, okay? So, and I've just drawn the difference in charge. So now my hair has a relative what charge? If it's lost all these electrons, my hair relatively has a what?
Negative, neutral.
No, come on.
Positive.
If it's losing electrical or negative electrical charge, now my hair has a positive electrical charge, and the balloon has gained electrons, so now it has a negative electrical charge. And so now these two things are,
Connected,
no,
opposite.
they're opposite, and therefore they
Attract.
attract. That's one of the most important principles of electromagnetism is that opposite charges attract. The implication there is that like charges repel. Opposite charges attract, like charges repel, and the very little example of my hair that you could kind of see it moving, that was the electrical attraction between a negative charge on the balloon, at least as I have drawn it, and a positive charge of my hair. Why might we call this static as opposed to current?
Because it stays there.
Yeah, it stays. That's the root of static. It stays. It's the charge that stays on an object. That's what static electricity is. The other example of static electricity you might have known is that when you're shuffling, this isn't carpet, so I don't even know why I'm bothering, but when you shuffle across carpet and then you go and touch someone, zzzt. You know that one? Zzzt. You do it to I'm sure if you have siblings, you have done that before. Something kind of cool is that sound is thunder. That is the exact same phenomenon as thunder and lightning. Like it's just the difference is, here's your boot and the carpet, and here on a different scale is the cloud and the cornfields. And as the boot moves over the carpet, it's picking up an electrical charge. Those are supposed to be electrons. And as the cloud moves over the cornfield, it's picking up an electrical charge. And later,
Wow.
when this object, later when this object touches,
The door.
this is your friend's boot, and this is a barn, that static charge is discharged. And that forms, in this case, zzzt, makes a little noise, right? And it makes a little tiny shock. Especially if it's nighttime, or I don't know, not necessarily, if it's dark, you can see it. Like when you have your blanket, sometimes, especially in the wintertime, sometimes you get your blanket and your leg hair, so I don't know. you take the blanket off, it's like, zzz. Did you ever notice that? Yeah, and that's lightning. That is literally lightning. And the same thing,
You get struck by thunder.
boom.
No, you get struck by lightning.
Yeah, so that sound is thunder. This sound is thunder. It doesn't sound like boom, but it sounds like a little baby boom. Crack, maybe. But those are the same phenomenon. That's the transfer of static charge. And that's as in-depth as we're going to get into that, because really, actually, the fundamental physics of that are kind of poorly understood. At this level, this is known, right? This is being taught to freshmen, and it's understood by freshmen. But the actual, quantum mechanical reasons why this occurs is a little bit tricky, and people are having a hard time grasping exactly what's going on, even in the scientific community.
That's why you should watch Bill Nye the Science Guy.
Mm-hmm. Yeah. So please be quiet, because remember, everyone can hear what you're saying. So if you have something important to add to the discussion, that's great. Otherwise,
Shut your mouth.
no thanks. Yeah. Your book calls this process, and this process, the transferring of charge, and then the necessary. By the way, if these have a negative charge because they've gathered up electrons, what must the charge of the ground be now? Positive. Or it has to have a relative positive charge. Same with the carpet. And this moving of electrons away, also these electrons will repel the electrons down here. So this negative charge repels the electrons. And the moving of these negative charges away is called charging by induction. This process is called induction. When the negative charges up here repel the negative charges that are still in this, that's called charging by induction. And that's why, hopefully, if you get a balloon charged enough, it'll stick here. No. Science has failed me again.
He's Cody's
We're in a
head.
simulation.
We're in a simulation. Electricity is broken today. I'm trying to charge by induction my sleeve so that there we go. Science is fixed, and it's a miracle. Look, the balloon doesn't fall down. Do you see that? No, it does not fall down. It does not fall down. The reason it's held there is because the negative charge has been imparted on the balloon is repelling the negative charges in my sleeve. Ridiculous.
And it falls.
There we go. Do you see them? Can you actually even see it at all in the video? No. So all that kind of happened more or less off screen. But the point is that the electrical charges, the negative electrical charges in the balloon or the cloud or the foot repel the negative charges in the hair or the ground or the carpet, and that makes them move away. And that makes the ground, carpet, and hair have a net positive charge. And that process is called induction. That's static electricity. Do you have questions about static electricity?
No, sir.
Do you know what thunder and lightning are now? Probably should. Current electricity, on the other hand, is the flow of electrons. This is due to charge difference, which we call, does anyone know off the top of their head what a charge difference is called? Voltage. It is usually called voltage. The difference in the charge is sometimes called electrical potential if we're trying to stay away from using specific units like volts, but it's called voltage. And the flow of those electrons itself is called current. And the resistance to that flow, this marker is not so hot. Sorry, Lucas, what did you say?
What?
Did you have something to add to this?
No.
It said like him.
Yeah, I know, I heard that. So the microphone, by the way. The resistance to the flow of electricity, the resistance to current, is called resistance. So it just keeps it nice and simple. The equation that relates all these things together is governed by what we call Ohm's law, and it's V equals IR, where V is voltage or electrical potential measured in volts. I is current or amperage measured in amps, and R is resistance measured in ohms, which is abbreviated with the Greek capital letter omega, which looks like that little guy. Somewhere maybe in your life you've seen something like this where there's a little triangle that has V, I, and R in it, and that's to help you manipulate the equation in order to calculate for current or resistance instead of voltage. But you already know how to do that, right? So I would say don't bother with this. You already know how to manipulate equations. If I wanted current to be by itself, what is my new equation? If I want current, I, to be by itself, what's my new equation? Divide by R. So V over R equals I. Right. But if I want resistance to be by itself, divide by I. I get
V divided by I equals R.
V over I equals R. It's not even that hard of an equation to manipulate. That little triangle thing that tells you, that helps you manipulate it, exists because this is an equation that we manipulate very often. And so even in contexts where people are not used to or comfortable manipulating equations, it still does need to be manipulated sometimes. And so that little triangle comes in handy for those people who can't manipulate equations. But you can, and so I would say just manipulate it as you have done with other equations. The path through which the electrons flow in current electricity is called circuit. A circuit is the path of electrons in their, path of electrons current. That's a circuit. The electrical potential, the voltage, can be provided either in the case of a direct current from a battery or in the case of alternating current from an electrical outlet like this one. So the source of the electrons for the electrical current can be either of those two things. Your book goes into fairly great detail about the different kinds of battery, and it talks about it also goes into fairly great detail about the way that alternating current works. But I'm not terribly worried about that. I am worried about that I kind of shoved myself into a corner here with my writings, but I don't want to go over here because then I block this stuff. Is everyone, no, not, let me erase the 4 fundamental forces of the universe. There we go, that'll give me some more room. And we are only now talking about current electricity. So there are two kinds broadly of circuit that we have. There is the series circuit and the parallel circuit. So in both cases, let me actually use the correct. This is the symbol we use in circuit diagrams for a battery. And in the series circuit, we would have the wire, which is just represented by a line. Maybe there's a light bulb, which is represented by this symbol. And then there's another light bulb. So we've got two light bulbs. A lot of Christmas lights. Hey, it's almost Christmas time, so this kind of works well. A lot of Christmas lights are set up like this. Now what happens if this light bulb burns out?
Get a new one.
You can get a new one. No. But what happens, okay, so when the battery's operating correctly, both of the light bulbs are lit up, right? That's a series circuit. If one breaks, the circuit is broken, all the lights turn off. This is really, when I said a lot of Christmas lights are set up like this, they used to be. This was terribly inconvenient because maybe you had a string of 100 Christmas lights, and now you have to go through and switch every single light bulb to see if that was the one that was broken. And God forbid there should be 2 that are broken, because then you might as well just throw the lights away. So instead of using that type of circuit called a series circuit, we instead oftentimes will use what we call a parallel circuit, where even if the electrical flow is broken to one load, we call the things that are being operated, the like a motor or a fan or a light bulb or a speaker, whatever's being operated by the circuit, we call that object a load. But we separate the loads into their own individual circuits. So now even if this light bulb breaks, this one still lights up. The cheap lights that I use for Christmas are kind of a combination of both. There's a series circuit for a ways, and then it starts over and there's a new series of circuits. So when one burns out, maybe 10 of them burn out, but then you only have to switch out 10 light bulbs to see which one's broken. Or if you're me, you throw it away and go get new ones from Dollar General that are lit in parallel. So this is called a series circuit, and this is called a parallel circuit. The last thing I think that we're going to touch on, and there is more in here, your book talks about fuses and circuit breakers, which are really just, those are both devices that if the voltage gets too high or the current is going too much, they will stop. They have no resistance up to a point, and then they will stop, they will break the circuit. That's why they're called circuit breakers if the voltage is too high. That way your house doesn't burn down or something. Like if your microwave starts to draw too much power, instead of getting to be 5,000 degrees, the circuit breaker will break instead. But the main thing the main other math we want to talk about is electrical power. You remember we had an equation for power. Do you remember the equation for power from back in when we were talking about work?
Work equals F times D.
Okay, yeah, but what about power? W over, yeah, like Tommy said, power equals W over T, or power equals E over T, power equals energy over time. Now we have a new equation for power, with electrical power, which is P equals IV. The power, P is power. What was power measured in back then?
Joules.
Mm-mm. Nope.
Volts.
Nope.
Watts.
Watts.
Same thing.
P is power measured in watts. I, we just said, is current measured in amperes. And capital V is voltage measured in volts. Now, we still will use the equation P equals E over T because sometimes we want to find energy. A common way to measure electrical energy is kilowatt hours, where we have power measured in kilowatts, we multiply it by time measured in hours, and that gives us an energy unit of kilowatt hours, which is a little bit chaotic, kilowatts times hours, and there would be a direct conversion between joules that we're used to measuring energy in and kilowatt hours. The energy company, NPPD, that provides the power to this community, measures the amount of energy they have dispensed out to you in kilowatt hours. That's how you're charged. So this is how we calculate power from the things of electricity. Do you have questions about power?
No.
It seems like you should.
Is it easy to do?
The math is pretty easy, isn't it?
Yeah.
We have 3 equations in this lesson that we're going to have to use. This one, power equals energy divided by time, which you will usually be manipulating to find energy. Power using current and voltage, which is P equals IV, and then Ohm's law, V equals I R.